Got the EMF in the last video using the rule integration of V cross B dot ds. Now we want to get the EMF using the rule that is related to the rate of change of magnetic flux. And we want to compare the two. Are they the same or not? They should be the same. We claim that you can prove in general that they're the same. So we're trying to prove that they're the same for this particular problem. So if you want to get the EMF, remember we said you have to choose a direction that you go around the ds vectors. So with this circle with this arc with an arrow means that we're going around the ds vectors this way. So that means you have to make the relationship between the ds vectors and the area vector for the area to be using the right-hand rule. If you put your fingers in the direction of ds, the thumb points in the direction of the area. So the area has to be coming out of the page for this to make sense, for this minus sign to make sense. So the EMF is minus d by dt of the magnetic flux. We want to prove that if you use this rule, you'll get the same expression for the EMF that we got using the other rule. So let's first get the magnetic flux. What's integration of B dot dA? What's the magnetic flux through this area? The magnitude of the first, magnitude of the second, times cosine of the angle between them. What's the angle between the area vector and the magnetic field? The magnetic field is into the page, and the area vector is out of the page. So the angle is 180 degrees. Cosine 180 is minus 1, and so you get integration of B dA times minus 1. The minus 1, I took it out. Now, if you look at the magnetic field here, or here, or here, or here, anywhere in the area, it's the same value. We assumed it's uniform in this problem. So I can take B outside of the integration. Get minus B integration of dA. What's integration of dA? It's the area of this rectangle. And the area of the rectangle is this length. It's a constant. L is constant. Times this length, which is varying because when the rod moves to the right, this distance gets bigger. So it's A is L times X. We put there phi then turns out to be minus B L times X. Now the EMF is not the magnetic flux, it's the rate of change of magnetic flux times minus 1. So the minus will cancel with the minus, so you get plus. The B times L, those are constants, they don't change with time. The magnetic field doesn't change with time in this problem, it's a constant. So B and L are constants, they can go out of the differentiation, the differentiation can go through them. And then you get dx by dt. What is dx by dt? What's the rate of change of this distance with time? Just the speed of the wire. So you just get the same result that we got before, that the EMF is BL times the speed of the wire.